Hello, welcome to this section of Circuit Analysis Tutor. Here we're talking about capacitors. We're continuing our discussion from the last section, and we're going to derive very briefly a lot of equations that we'll be using in a lot of analysis here to come. And it's going to be a little bit faster than it was for inductors because all of these equations look very similar. You'll see as we go along. So the first thing we want to do is we want to develop a relation for the voltage across a capacitor in terms of its current. Notice that we've already talked about the current I is equal to C dV dt. Now we want to turn that around and solve for voltage. And we did this kind of thing with inductors as well. So here is a capacitor. We'll just kind of draw it for reference. And the voltage across that capacitor, actually let's just say here's the current going through it like that. Then that means the passive sign convention, that would be the voltage. Now we have already established in the last section that the current flowing through this capacitor is a capacitance C times dV dt. So this is the current flowing through the capacitor if we know how the voltage is behaving. What we want to do is turn it around and solve for the voltage. And so what we're going to do is that right now. So what we'll do is we'll move this dt over. So I times dt is equal to C times dV. All right, and then we just move it as if it were a fraction. And then we divide by the capacitance. So I times C dt is equal to dV. Now let's flip around the equal sign because I'm solving for V, so I want it on the left-hand side. Let me switch colors. So basically dV is equal to I over C times dt. Now what do you think we do next? I'm trying to find a function for the voltage. It's wrapped up in a differential, so I want to integrate both sides. I can do whatever I want to both sides as long as I'm consistent and do it to both sides across the board. So when I integrate dV, you get and recover your V as a function of t, which is what I'm trying to find. And then over here, the 1 over c is a constant. So the 1 over c, it just comes out of the integral. And then I'm integrating I dt. So this will be the integral of 0 up to times t of I of t dt. Now, I'm doing this integral, but then you always have a constant of integration when it's over, and so that constant of integration is going to be the voltage at time 0. So this is the voltage in terms of current. So in other words, for a capacitor, if I already know the voltage behavior, I can calculate the current by that derivative. When I flip it all around and solve for the voltage, then if I know the current and I know the initial value of the voltage, I can just integrate the current and then bam, I recover the voltage. So this equation shouldn't look all that foreign to you. It's exactly the same equation we had for inductors. When we had V is equal to L di dt, and then we turned around and solved for I, it pretty much looked exactly like this, except this was 1 over L here, this was a V of t in here, and this was I, the initial current at time 0 there. So it's basically the same thing. The reason it comes down to be the same thing is because it's got the same relation. I think it's kind of fascinating, really, that we can create these two different circuit devices, that one of them behaves on magnetic fields, one of them behaves on electric fields, and all the equations really look very similar. It's just you kind of flip the component. If it's voltage, you might switch it with current, and current, you might switch it with voltage, but other than that, they look the same. To me, that speaks a lot as to the symmetry in the magnetic fields and the electric fields in nature. So keep this in mind. You might have to integrate the current through a capacitor to basically give you that voltage. Now, I'll give you a little bit of insight. Why do you think it's actually this way? Well, we talked about the fact that the voltage here really is just an artifact of the piling up of these charges. When the current comes in, it piles up, and then it gets bigger and bigger and bigger, and that's what's causing this voltage here, the positive being here and the negative being here. So really what you're doing is this integral is adding up the current as a function of time. What do you remember back to the units of current, right? An ampere is a coulomb per second. That's charge flowing. That's what current is. So when I integrate current over time, what I'm really doing is I'm adding up all the charges that are coming. If you kind of use this as a boundary and you have a wire flowing, current's flowing through this wire, then so many charges per second are flowing across this boundary. That's what an ampere is. It's coulombs per second, right? So when I integrate this current over time, I'm really adding up all of those charges that are piling up into the plate. And of course I've got a constant out here, and then I add to that whatever initial voltage I had when I started my little experiment. When I get the sum total of that, it arrives at the voltage at time t. So however, if you integrate longer, you're going to get more charge buildup, so you're going to have a higher voltage, and that's what's going on here. That's why it's an integration. All right, the next thing we want to derive or talk about is power. So let's talk about power in capacitors. And in just a moment, we'll talk also about energy stored in a capacitor. But for now, recall that power is I times V. It's always true. Current times the voltage. Now, the current in a capacitor, current is C dV dt. So I'm going to put it right in here. So I'm going to say C dV dt. And then I still have a voltage out here. So the power is C times V times dV dt. So this is the power when you know the voltage. So this is power in terms of voltage. So if you know the voltage behavior across a capacitor, if you know V as a function of time, you just happen to be given that, then you can multiply this times its derivative times its capacitance, and then you have a function for the power as a function of time. And if you want to evaluate that power at a given time, you can evaluate it at a given time, and then there you know, so many watts of power at that time. And again, the power can be positive, which means we're delivering power to the capacitor, or it could be negative, which means the capacitor is delivering power back to the rest of the circuit. So it's a storage device, into the bank, out of the bank, like that. All right? So this is useful if you know the voltage and you're trying to find the power. Let's turn it around and go the other way. Let's say P is equal to IV, but now we know what this voltage is. We already found what the voltage is across the capacitor is equal to this guy. So it's I times 1 over C integral 0 to T I of t dt plus the initial voltage. All right, so this is the power in terms of current. So if you have a capacitor and you know the current characteristics, you know what I of t is, then you would just integrate it. You have some initial voltage, usually at 0. You have a capacitance here, 1 over that. That's a constant. We already know what the I is, so we can calculate, again, the power relationship. So no matter what we do, we're getting the same thing. If we know the voltage characteristics and we calculate P as a function of time, the power, or if we know the current characteristics and we calculate this power, ultimately these two things are going to be exactly the same thing. It just depends on what you're given in your particular problem. And in both cases, notice that they're basically the same exact equations that we got for inductances. If you go back to inductors, you'll see that this looks incredibly similar to what the inductor relationship is, and so did this thing. All right, so finally what we want to do, before we close this section out, is we want to know what the energy stored in the inductor is. So we'll recall that power is energy flow, which means energy per unit time. And I've already written this a lot, so this is dW dt, energy flow per unit time. So what that means is that P is, from before, the power we already got, C times V times dV dt. C times V times dV dt. This is what the power is in a capacitor. So this is the power flow as it relates to a capacitor, and we're just saying above that power is always equal to the derivative of energy per unit time. And what we're trying to find now is how much energy stored in this inductor. So we want to find what W is. So really we're trying to solve these two things. We've got a dt on the bottom in both cases, so they kind of cancel out. I can multiply both sides by dt. So what I'm going to get is dW is equal to C times V times dV. Notice that's what I've got. On the one side I've got dV, on the other side CV dV. And so in order to get anywhere, I'm going to integrate both sides. So the integral of dW is equal to the integral of C times V times dV. So what I have when I integrate, on the left is just going to be energy, W. Here, the capacitance just comes out. I'm integrating v dv. That's just like x dx from calculus. So what you get is 1/2 v squared. So W, rewriting it 1/2 CV squared. This is the energy stored in capacitor. And there it is. And this is the energy in joules, right? This is the energy in joules. And this is the power. These are power. These are in terms of watts. So notice again that this is exactly the same as the relationship for a inductor. For an inductor, it was 1/2 L times I squared. Here for a capacitor, it's 1/2 C times V squared. And that just kind of goes back to the physics. When you talk about inductances, the energy stored in the magnetic field comes from the current flow. So it's 1/2 Li squared. It goes as the current squared because current's generating the magnetic field. Here it goes as 1/2 CV squared because in a capacitor, the energy is stored in the electric field. The electric field comes from the charged particles, which arises as a voltage across those plates. So that's why it goes as V squared. But it ultimately has exactly the same form. And notice that this power relation, CV dV dt, and also this integral here, if you go back and look, is exactly the same form as it was for an inductor as well. So you can again think of them as peanut butter and jelly. You know, one deals with magnetic fields, one deals with electric fields. Those characteristics are going to be used over and over again in circuits. Now I will say though, both of them are used in circuits, but you will see that capacitors are probably a lot more prevalent in a typical circuit than an inductor is. The reason is because inductances are kind of big and clunky and coils of wire and just kind of like physically take up large space. Capacitors can be built small and mounted on a circuit board. You don't have this coil here with the thing in the middle. They can be built much more compactly. So when you open up a typical circuit, you'll typically see more capacitors, but inductors are used everywhere as well for certain applications. And in our discussion of our roadmap of circuits here, what we're going to do is take the capacitor and solve a couple problems here with just capacitors, give you an idea of the relationship between current and voltage so you can kind of get the hang of that. And then what we're going to do is learn how to solve simple circuits with arrangements of capacitors and inductors. And then eventually we're going to get to AC analysis where we have alternating current, and I'll show you how to deal with all that stuff as well. So we're building our skills one step at a time. Each skill that we have in the past builds and builds and builds, just like we spent a lot of time with the inductor, really drilling it in. Then when we go to the capacitor, it's not quite so hard to swallow because, you know, it's very directly related as far as the equations go. And you can kind of, I think, wrap your brain around it a little bit more. So pat yourself on the back. You have a good understanding of capacitors. You have a good understanding of inductors from the previous sections. Follow me on to the next section. We'll do a couple of problems that deal with voltage and current relationships through a capacitor.